So, hi everyone again. So, in my last lecture, I talked about, let me take this on. I talked about the FIDISOL, the solver itself. We talked about how it works and what the several steps that we have to take in order to start from a theory of gravity and then getting some solution to that theory. Let me start this again. So, in this lecture, I'm more inclined to talk about having already a solution, and then what you do with that solution. So imagine we have a theory, you obtain a solution, now what you do with that? What can you do with that? So here I'm going to just show you some things that I usually do in order to obtain, for example, the mass, the angular momentum, some, for example, light rings, as Pedro was already talking about, and other things that you can extract from that solution. And for that, I will talk about something that already many people talk about, so boson stars. These are, as already was said in other presentations, horizon plus, self-gravitation, solitonic-like complex scalar field solutions of the Einstein-Klein-Gordon action. I have here the action, and is basically just the Einstein part, the geometry part. I don't have here the pointer. So it's basically the geometry part plus some complex scalar field where you have the kinetic term and some potential. Here, this potential can be a lot of things if you want to explore. But here, at least in this talk, I will just mention the most canonic type of potential, which is the mass term. And then you can add, for example, self-attractions. Or there's another work that we did as well where we consider an axion-like type of potential. But here, I will just focus on this more simple case. So in this case, what we will get is the so-called spinning mini boson stars. So in order to obtain them, I can do just a quick recap. You start with the action. You then introduce some ansatz. There you can find the solutions. So here, in this case, okay, so you can start with this specific ansatz. So obviously, the boson stars are a bit different from the Kerr case that we talked about yesterday. Mainly, they don't have an horizon. So this, in this case, can be quite easy to impose by just saying that if you take the previous ansatz and put RH to 0, you basically saying that there is no horizon. Then, obviously, in this case, there is a scalar field. So you have to have some new ansatz function that can connect with that part, with the scalar field. So there will be another ansatz function. Instead of only having 4, you have now 5. And then in this case, just to simplicity and some, in this case, it helps a bit the solver to get more accuracy. We also redefine the double function as W over R. You could also do this for the Kerr case. You also can get a solution like that with that type of ansatz. But here, well, at the time we didn't do it, but here it helps a bit. So in the end, you have this new ansatz. As you can see, we have again we have the 4 usual ansatz functions, F0, F1, F2, and W. But now we also have this new ansatz function phi for the scalar field. We also see that there is no n function that appeared before. So basically, that's because you put RH equal to 0, and then the n function will be equal to 1. So it disappears from the metric. And there is some new part here regarding this exponential for the scalar field. So in order to have boson stars, complex boson stars, we can violate the Bekenstein theorem, like Eugene yesterday talked about, by imposing that the scalar field does not have the same exact symmetries as the metric. So the scalar field depends on the time and the azimuthal coordinate. And you can do this, but you have to impose, and we have to be careful, that at the level of the Einstein equations, the part from the geometry do not depend on the time and the azimuthal coordinate. So the energy momentum tensor must also not depend on those coordinates. And in order to do that, you have to take this exponential. You have to take this form for the scalar field. With this, there are new 2 input parameters, which is that omega and m. So omega is the angle frequency of the scalar field, which will be an input parameter that you can change. And there is also this m, which is the azimuthal harmonic index. And here, this only takes all integers. Can be either positive or negative. And this is also input parameter. But here, at this case, at the solution that I will show you, this m is fixed to 1. So if you want to obtain the rest of the solutions, you only change this omega, the angle frequency, and you can get that X spiral that some of the talks already, some people already talk about. Now, since you already have the ansatz, you can now look at the field equations and then also to the boundary conditions. So in this case, already talked about the boundary conditions for the other functions in last lecture. So here I will focus more on the boundary conditions for phi. So asymptotically, you don't want to have any scalar field, so the phi must go to 0 as you go to special infinity. At the axis symmetry and regularity, you can again do that type of expansion that I showed in the previous lecture and see that phi must be equal to 0 at these axes, so at the poles. Again, as in the Kerr case, there is a Z2 symmetry, so there are two hemispheres that are equal, so the north hemisphere is equal to the south hemisphere, so you can integrate everything only between 0 and the equatorial plane, or pi over 2. And then you also impose that the derivative of the functions and also the phi must be equal to 0 at that equatorial plane. Finally, we have now the origin boundary condition. It won't be at the event horizon, obviously. There is no event horizon. So we have a boundary condition at the origin. If you do, again, the power expansion, as I showed before for the Kerr case, you can show that this phi must go to 0 at the origin. There's also a key point here that I don't show here, but since we also redefine the function w, and since the w now, the boundary condition is at the origin and not at an event horizon, the double function won't go to the horizon angle velocity, but it will go to 0. So there's a new boundary condition for that w function at the origin that I don't put it here. Now, obviously you have some new equations of motion, since now you are on Einstein-Klein-Gordon theory. So if you compute the equations of motion, you get this function or equation that you have to solve. So here we have the Einstein tensor that will be equal to some energy momentum tensor associated to the scalar field. Then you also have a new equation, the Klein-Gordon equation, which is quite, well, the usual type of equation that one found. So here, okay. So the energy momentum tensor now is, well, it has this form. Here I expanded it a bit, so it's a bit bigger. Usually they contract some terms. But with Mathematica, you can easily put it there and compute this energy momentum tensor. Now, since there is this mass of the scalar field, this mu, it's useful to rescale everything to the mass of the scalar field. So we can do some rescales of the variables. So just the R variable, the omega, for example, and well, here is just redefining phi over a constant. But mostly these two quantities are quite useful to do. So everything is redefined in terms of the mass of the scalar field. Now, so you have the ansatz, you have the equations of motion, you have the boundaries. So in principle, you can then compute the Jacobian as well for the solver. You can put everything on the solver, run it, and find one solution. Obviously, here there's some subtlety in terms of, for example, the initial guess. So for this case, in the case of Kerr, since you have already the analytical metric, you could use that as an initial guess. But here you don't have anything for the spinning boson stars. You don't have an analytical solution. So what do? In this case, there are some, you can compute the spherical mini boson stars that already Juan Carlos talked about, for example. And in that case, what you have is that it's connected to this one when this m is equal to 0. So you can start with that solution. So, for example, you can use a more range-good method with a shooting method, for example, to obtain the static solution, which is basically m equal to 0. And then you can start with m and slightly change the m for a fixed frequency. So you start at 0, then you go to m equal to 0.01, for example, and then go up until it reaches the point 1. So at the level of physics, this only makes sense when m is an integer. So integer or a whole number. So 1, 2, 3, 4, and so on. But at the level of numerics, the solver doesn't care if m is an integer or just a real number. So you can go from 0, go up all the way up to 1 very slowly, so the solver can converge. And then when you get to 1, you are on the point that you want. You have a spinning Bose star with m equal 1 and a fixed frequency. After that point, you can then fix m to equal to 1 and then start changing the angle frequency and you get the well-known X spiral. So if you do this, you can do everything. I won't show it here specifically, but this part a bit more interesting how to extract information from the solution. So imagine that you have a solution and you have something like this. You have a lot of files. That's basically the output that CADSOL does or give you. The most important files are usually the ones that start with a F. So for example, this one. This is f/0. What this means, or what it has, are the functions, f1, f2, f0, w, and phi, computed at the origin. So the /0 means the origin. So these are the values of the function exactly at that boundary. And for example, this f/infinity is the same, but the functions are computed at infinity. Then you have the t0, which is in theta equal to 0, one of the axes, and pi over 2. Then you also have the derivatives of the function. So, for example, if you have fx, this is the derivatives, the radial derivatives of the functions, in this case, computed at the origin. Then you have all the others, which will be the radial derivatives, the theta derivatives, and also the second derivatives. Then there's also this func funstf data file function, which basically have all the functions computed at all the grid points. So all the information for the function are in this file. And you will see that it will be important. Then you also have the grid, so grid in the radial direction and in the theta direction. Also have the output, which is exactly the same that I showed the last lecture. And we also have, for example, this Ricci data, which has the Ricci scalar, the two constraint equations, and the Kretschmann scalar. So you can use this file, plot everything to see if everything is smooth, if everything is right, and to evaluate the solution. Then you have this last T44 data, where it has some of the energy momentum tensor quantities for all the grid points. So here you can use it, for example, since in this case this is a boson star, you can use this to compute the Komar mass, for example, the Komar angular momentum, or you can use that to verify the energy conditions, for example. And I will show you that. So you have a lot of files. Now the question is what you do with them. So with that you can go to Mathematica, for example. I started with Mathematica in the beginning, but since Mathematica is very slow at going through all the solutions, I decided then to use this in C, but it's easier to show in Mathematica, obviously. So first thing I do usually is just, again, clear some variables. If I have other Mathematica files open, this way everything is erased and I start new. Then you start to extract data from the files. So this first line is just to define the secretary for the Mathematica, so to go to the directory where you have all the files. But, well, it's important. Then you can start to get some information, for example, for the input parameter. In this case, since I fix m equal to 1, the only thing that changes is the angle frequency. And this is stored in this rest.txt file that was in that directory. Here you can then go grab the value of omega, so in this case it's just 0.7. Then you can extract the grids, since it will be important then to do some interpolations. So you have to know what was the grid that you use. You can see how many points that we had in each grid. For example, here we have 401 points in the radial direction, 40 points on the theta direction. And then you start to extract the file, the functions. So I start to define just how many functions there are. So in this case, they are 5. In the Kerr case, there are 4. But if you go, for example, for a Proker star, they are, if I'm not mistaken, 8. 7 or 8. One of the two. And then I read here the func data file. So it's where all the functions, the exact functions are for all the points grids, all the grid points, sorry. And then just just redefine. Here I just basically constructed three-dimensional matrices. So basically, the idea is, in this case, basically, well, yes. So it's just to do a 3D matrix. So here we'll have the theta points, the r points, and then in this third direction there will be the 5 functions. You do this so that then you can have matrices for each one of the functions. With this, in this file I also put some parts that only apply to the black hole case. So for example, here for the boson stars you don't need to extract information from the origin, because you don't get anything from there. But in the case of a black hole, you can extract information of the horizon, because then you can compute, for example, the Hawking temperature, the horizon area, and others. So I also put it here in the file, then I will send you this as well, where you can extract information from the horizon. So the horizon in the case of the boson star, or the origin in the case of the boson star, or the horizon in the case of the black hole. Then you can extract as well the Ricci and the Kretschmann scalar. So that's it. And the same for the energy momentum tensor. So this is basically almost equal. So I won't take too much time on this. But then you can do the nice part, which is plots. So for example, here we have a plot for the F1 function. Here I use the compactified coordinate, x. So 0 is at the origin, 1 is at infinity. And you can see 3 lines for different values of theta. It poles pi over 4 and the equatorial plane. And you can see, well, it has this profile. So far you don't extract a lot of information from here. You just can see that everything is smooth. So there's no divergences, there's no very pathological types of behaviors. So you can see for the phi, the w, and so on. You can then look at the Ricci, for example. Get this. You can look at the Kretschmann, for example. You get this, and you can see that you don't have divergences, everything is smooth, so everything appears to be, or to work well. Then you can also do the same for the energy momentum tensor, or some of the components of the energy momentum tensor. So this one's only plots. But now we can start with starting to get some physical quantities. So the first one, that the usual one tries to get, is the mass in the angular momentum. This can be done by doing a symptotic behavior, so looking at the symptotic behavior of some functions. So since this is symptotically flat, you can do this type of connection, that symptotically flat, the GTT part of the metric has some information regarding the mass of the object, and the GT phi has some information regarding the angular momentum of the object. So if you do an approximation asymptotically, you can then see that the f function is the one that has some information regarding the mass here, and the w one is the w function is the one that has some information regarding the angular momentum. So if you do a simple linearization of f in order to 1 over r, you can get the mass. And if you do a linearization of 1 over r squared for the w, you get the angular momentum. So quite easy to do. A different way to do this, since we in this case we have a boson star, is looking at the mass in the angular momentum through the Kolmar integrals. So these are these two integrals, quite famous integrals, where you can basically integrate everything in the space-time. In this case, since the boson star, it goes from the origin up to special infinity. And you can compute these two quantities to get the mass and the angular momentum. So in particular, in the end, what we have to compute is these two integrals. And these quantities in blue are two of the quantities that they are saved on the T44 file that I showed before. So that's why we save those types of terms of the energy momentum tensor. again, since this is a Boson star, there will be, you can check if this result is exactly the same as the one for the mass when you do an asymptotically study. So you can then go to Mathematica again. So from the asymptotics, you then, this part here is doing exactly that type of linearization. You get the F0 term. You go to the last values, so symptotically far away from the solution. You then do a linearization. Here, I think Mathematica has to have at least two terms, so 1 over R and 1 over R squared. So here I use X, but that's the same idea. And then get the coefficient for the 1 over R part. And then you can do, a mean for all the angles. Instead of only looking, for example, the equatorial plane, you can do a mean for all the angles that you have. Then you do the same for the W function to obtain the energy momentum tensor. And at the end, you do a mean, and you get the mass and the angular momentum computed at some asymptotically far away from the object. So asymptotically behavior of the function. You can also do, then, as I said, compute the mass and the angular momentum through the Komar integrals. So this is a bit more tricky to do, since we have to do double integration. You can do first on the angular part and then on the radial part, or vice versa. But here you can go to those slides and get the expressions, and then try to do a table, so to do interpolation, to do an integration. And you do that on the theta part, and then you get that result, and you do the same for the radial part. And at the end, you'll have the mass and the angular momentum computed through the Komar integrals. As I said, in the case of a Boson star, these two values computed at the asymptotic behavior or through the Komar integrals must be the same. Something that I also do here regarding to a different quantity is to save for each radial point, which is the mass at that integral. Because then you can have a mass function that says how much mass is within that radius. And this will be important because of something that we call the compactness. So for a Boson star, the Boson star doesn't have a well-defined surface. It's something, the scalar field decays exponentially as you go far away, but it doesn't have a rigid defined surface. However, you can try to define some type of surface which is associated with the radius that contains 90% of the total mass of the Boson star. So you can compute the perimeter radius, for example, that contains that 90% mass of the Boson star. And this perimeter radius is just is not exactly the radial coordinate, but has some significance. And basically, it just says that at the perimeter radius, the circumference around that in the equatorial plane will be exactly 2 pi times this perimeter radius. So it's a more well-defined quantity, is more geometric as well. So as soon as you have the radius that contains 90% of the mass of the Boson star, then you can compare it with the Schwarzschild radius, basically. So the 2 hem. So in this case, since we are using the mass of the 99%, the total mass, then it makes sense to use 2m of those corresponding to the 99% mass of the Boson star. Obviously, well, you can then do that in Mathematica. So in this case, it makes sense to save all the masses for each radius, since then you can see exactly at what radii you get the 90% of the total mass. You then can do an interpolation and find exactly where is this radius. With that, you can then compute the compactness, which basically is here, and see if the Boson star is super compact or not. Another thing that some Boson stars have, not all of them, are egoregions. So some people already talk about a bit of egoregions, but essentially they are regions where the norm of the time-like killing vector becomes positive and are bounded by a surface where this norm vanishes. So the square vanishes. And essentially, you just have to see where exactly the GTT part of the metric vanishes. And this will define the surface. So for a curved black hole, this is a well-known figure. In this inner part, we have the horizon, and this outer shell is the well-known ago surface. And the ago region will be this region between the horizon and the ago surface. This is well known. This is the case for Kerr, but for boson stars, they are quite different. So as you can see, the ago region for this case even changes topology. So it's no longer a spherical topology, but it is a toroidal topology. So you can look and see if our case or our boson stars that we have has ago regions. And for that, you only have to look and see if GTT is equal to 0. So that's exactly what you do. You can write GTT through the Z functions. You can also do a plot, for example, and here you already can see that indeed there is an ago region. There is this part here where, for example, in the equatorial plane, the green line, we see that from this point up to this point here close to the origin, the GTT part of the metric is positive. So there is indeed an ago region for this case. You can then confirm this by doing some quick computation, that if you look at the equatorial plane, you can try to see how many zeros the GTT function has. So in this case, it will have 2. And then you can also try to find where this, what is the radial coordinate for the beginning of the ago region and the end of the ago region. Now, now I would like to give you a mini course on my mini course about the structure of cycloorbits. So Pedro already mentioned in this first lecture how to obtain light rings. But here I also will talk about that, but also about time-like cycloorbits. So what you do is that you assume there is some test particle in geodesic motion. And in order to study the cycloorbits, assuming that it is a cycloorbit, you have to consider, for example, the effective Lagrangian. For example, Pedro, in his talk, in his first lecture, assumed the Hamiltonian. But here, I usually start with the Lagrangian. Since this is on the equatorial plane, there will be no theta variables. You fix theta. So if you expand the Lagrangian, you get just the terms in the time, the azimuthal coordinate, and the radius. Then there's this Xi quantity that is either equal to 0 for massless particles, so light, and if you compute this, you get the light rings, or it can be equal to -1, where you can study the time-like case or massless particles. So you start with the Lagrangian. You can use the symmetries of the solution, mainly stationarity and Isaac symmetry, to compute the energy and the angular momentum of the test particle. And it's related to the Killing vector fields. With that, you can rewrite this Lagrangian and define this potential in this way. And you do this because now, if you want to compute or to find the cycloorbits, the variation of the radial coordinate must be 0, so r dot must be equal to 0, so you have to find the zeros of this potential, as well as the variation, or the r dot dot, double dot. And that, basically, if you expand, you will see that that means that the derivative, the radial derivative of that potential must also be 0. So, in the end, what you have to see is that, okay, the potential, its radial derivative at some cycloorbit must be equal to 0. So, in the end, what we have to do is solve these two equations simultaneously. If you do so, you will find the cycloorbits. You then can look into the radial stability by just seeing for a cycloorbit what is the sign of the second derivative of this potential. If it is negative, it's a stable cycloorbit. If it is positive, it's an unstable cycloorbit. Now, this is the usual recipe to find cycloorbits. But here, I did not specify yet if I'm talking about light or no particles or time-like particles. So if you now fix that part, so let's start with a massless case. So C equals to 0. This is exactly the same as Pedro already mentioned. You'll get essentially the light rings. So you can start by defining or introducing the inverse impact parameter, where this plus and minus corresponds to the prograde and retrograde orbits. Since there's rotation, we have there will be two types of orbits. And the first equation gives you an analytical expression for the inverse impact parameter, and the second one will give you the radius of the light ring. So if you find a 0 for this equation here, it means that you have light rings. You then, if you have some light rings, you can look into the radius stability by looking at the sign of the second derivative of the potential, and essentially is the same as before. If it is positive, it's unstable. If it is negative, it is stable. So for the light rings, the only thing you have to do is essentially this. For the massive case, so the time-like particles, it's a bit trickier, but you can also do the same. So for that, in order to simplify the equations, you can introduce the angular velocity of the time-like particle on a circular orbit. And with this equation and the first equation, so potential equal to 0, you can find the energy and the angular momentum of the time-like particle. This will be written, however, in terms of the metric functions, the angular velocity, and this beta function here. And just to give you some quick intuition why this beta function appears here, this beta function is associated with the type of orbits that you can find. If for some reason this beta is positive, then you have time-like circular orbits. They can be either stable or unstable, you don't know yet. You have time-like circular orbits. If this beta is equal to 0, you are exactly on a light ring. And if it is negative, you are on a region where you find space-like circular orbits. So it won't be a natural matter, it will be something very exotic. So this beta function is quite an important function that appears here. Now, with the second equation, the derivative one, you can find an analytical expression for the angular velocity. So now everything is well defined only in terms of the metric functions. In the case, well, in general, I would say this angular velocity is always real. But if you look closely, there's that square root with some quantities within them. And in particular, for the case of boson stars, spinning boson stars, that is, that quantity can be negative. And I will show you next that, in fact, it will be negative at some region. When that happens, this angular frequency will start to be complex. And in fact, what you have is a region where you don't find any circular orbits. Neither time-like, neither light rings, neither space-like. You don't have anything related to circular orbits. And this will be the case for the boson stars, as I will show you. Now, if you compute this, you then can find the radius stability of the circular orbit. Again, you have to solve that and see if it is positive or negative. So you can do exactly that. So for here, what I did was to define the metric part of some metric components. So interpolate those functions, so that to use the results that I showed. Instead of using directly the ansatz functions, I use instead the GTT, GT5, and GT5 terms. So this is only just to do the interpolations. And now let's look at the light rings. So for the prograde case, this is positive. And then you have here the inverse impact parameter. You have here the equation that if it is 0, we have a light ring. So you can do a plot of that. And here you can see that it's never negative. It's never equal to 0. So indeed, for this boson star in particular, in the prograde case, you don't find any light rings. And you can confirm that, for example. You can just look if there is indeed some 0, and you will find that there is none.
This is a rotating boson star.
Yes. Okay, then you can do exactly the same for the retrograde case. So now here we have a minus. Then you can again do the plot and see that in fact for this boson star, for the retrograde case, there are a pair of light rings. So this is in agreement with Pedro's lecture. So there is in fact these two light rings. You can then try to see where they are. so the radius. So here again, you can confirm the number of all light rings, and you'll find that they are 2. And then here you can try to find the radial coordinate where the light rings are. Since there is light rings, you can look into the stability, just compute this and see if it is positive or negative. And here I just have a small code just to say, yeah, okay, the inner one is stable and the outer one is unstable, again, in agreement with the lecture from Pedro. Now, you can then go further into the time-like orbits. So here there will be a bit more functions. So you can compute first the angular velocity of the time-like particle. So this is for the prograde case, so a plus. You have here the beta function for the prograde case. And then you can define the energy in the angular momentum. You can then plot it, for example. And here you can see that, okay, so this is well defined, but suddenly there's this inner region where you don't find any value for the energy and the angular momentum. So you start to see, well, what is going on? Supposedly you could find the circular orbits all the way to the center. And what happens is exactly what I said before, that the angular velocity starts to be complex. So if you take what's within the square root, so this quantity, you can see, in fact, that it's always positive, except very close to the center. So it starts to be complex. The energy, the momentum starts to be complex. So that's why when you do the plot, anything appears on that small region. Okay. So here, I just find where is this point where this function starts to be negative. And then you can now look into the stability of the rest of the regions. So where you can find cyclic orbits, time-like cyclic orbits, you can look at the stability. And in the case of the prograde orbits, all of them are stable. So this second derivative is always negative, therefore they are always stable up to infinity. If you, now you can do, okay, here is just to show that, okay, there is no 0 for that second derivative. So it's always negative and therefore is always positive. Okay, since in this case you have always stable cyclic orbits from infinity up to that inner region where you don't find cyclic orbits, then the ISCO, the innermost stable cyclic orbit, will be exactly at that point. You can have stable time-like cyclic orbits all the way down up to that point where the angular frequency starts to be complex. So I don't know if they...
But this isn't an ISCO, right? Properly saying, because the orbit is not unstable.
But it doesn't have to be. It's the last, or the innermost, stable cyclic orbit. Because within that you don't have.
But it's different from the Schwarzschild
yes,
case that is marginally stable.
Yeah. Okay. It's different from the usual statement that the ISCO would be the change between the stabilities. So a stability region with stable cyclic orbits, and then start to have a region without or with unstable ones. So usually people use that to say it is the ISCO, but in this case it's not.
So then what happens when you push a little bit this, or when you move a little bit this orbit? So if you change your parameters a little bit, does it stay around that region in an eccentric orbit, or do you know?
Exactly, no. But if you perturb it, that limit, it's technically stable, but if you perturb it in the direction where the DC function, or this function starts to be negative, so starts to be complex, angular velocity, it will not be a cyclic orbit anymore in that part. But I don't know exactly how it evolves. If it falls to the center of the star, if it has some type of elliptic orbit or other type of orbit, I don't know exactly. But technically, it's stable right into the limit. But if it goes within, you have probably some type of different orbits. But if it goes again outwards, it can then start to be stable or circular again if it has the right energy and the momentum.
Probably, yeah.
Yeah.
I mean, and it's probably very similar to Newtonian arrival kind of distribution. That's interesting because
So, but that's very interesting because it means that you cannot go up to the center of the star through a sequence of or circular orbit, which is usually what one does when you consider this adiabatic approximation. So what, in the end, you have this transition, but it would be maybe interesting to investigate what happens when you have an emitter going spiraling.
Yeah, that is what we are looking now. And in fact, if you assume just the MRIs, so adiabatic evolution through emission of gravitational waves through the Quadrupole formula, what happens in the boson star is that the particle never reaches this point. So basically, it starts to in spiral, starts to accelerate, but then as it goes close to this point, it starts to take an infinite time to reach that point. At least is what we saw so far.
But I would like to comment on that. Yeah. So, but you see, the problem is that the stars are unstable. The rotating boson stars.
The spinning boson stars.
So, yeah, that's what we are,
We can also look into the self-interacting.
About 1,000 light crossing times, so it's not too large.
Okay, so the particle cannot.
Yeah, so I mean, that kind of analysis is of course interesting, but from the viewpoint of phenomenology is less interesting. That's my point.
But boson stars with self-interaction
not so toroidal.
True, but you can also try to see this and see if there is this type of region.
But probably this is very much related to this toroidal structure.
No, yeah, I know.
So, and when you include self-interactions, they become much more spheroidal.
Okay. But we will be interested to see if this also appears.
And probably there will be kind of limiting.
Yeah. It will be quite interesting. So, in this case, that's orbit where the angular velocity starts to be complex. We call it, in this case, since it's connected to a stable region that goes up to infinity, the I-score. So you can do some, plots or some illustrations, sorry. Not this way. Okay, down. Okay, here. You can do some type of illustration. So basically, this is the R coordinate. So here it's the origin. It goes up to infinity, but here it doesn't matter to go very, very far away. But you see that there is an inner region where you don't have circular orbits. And then after that point, up to infinity, you always have stable time-like circular orbits. Then you can do exactly the same type of analysis for the retrograde orbit. So you do everything again. And again, if you plot the energy in the angular momentum, you see that, again, there is this small region here where everything no longer is defined. So this is obviously, it can be quite simple to see because if you look at the expression for the angular velocity, this expression within the square root is exactly the same, independent if you are co-rotating or counter-rotating. So this will always appear, at least for spinning boson stars. So again, you can do exactly the same. You see that the parts within the square root, again, is negative at some inner region. Sorry. And you can do exactly the same, but now you can look at the stability of the rest of the time-like circular orbits. And here you can see something that's different. So in this region, where this is positive, you have now a region of instability. So time-like circular orbits there are unstable. But then there is this very small region here that's also stable. And although it doesn't seem, if you look at the part that is further away from the star, we see that, okay, so close to R equal 4, close more or less, is where the unstable region starts. So this starts to be positive, and from there, that point up to infinity, this is negative, so we have always stable circular orbits. So in this case, you can see that the structure is more rich. So again, you can try to find some zeros, how many zeros the derivative has, the second derivative has. So in the end, you can do again this type of illustration just to have an intuition. So if you are far away, you are on the stable region. Then you go closer, you will find the unstable region. And then here, in this point in this, are the light rings. So this is the outer light ring that is unstable. This is the inner light ring that is stable. Within the two light rings, you don't find time-like cyclic orbits. That's where the beta function that I mentioned starts to be negative. So indeed what we have there are space-like cyclic orbits. If you look closely, or more closely, to the center of the star, you then see, so you have the region where you don't have time-like cyclic orbits, we have the inner light ring, then we have a very small region of stability, and then again the region without cyclic orbits, where the angular frequency starts to be complex. So here, for example, we have two types of ISCO, let's say. You have the absolute ISCO, or the ISCO in the sense of the definition, which is this one, because it's the innermost stable cyclic orbit. But you also have a relative ISCO, or marginally stable cyclic orbit, which is this one. So here is the point where the stability changes, and that's what most people associate with ISCO, and that's the usual case. But here we have these two types of special orbits. But okay. The last thing that I want just to talk in the last minutes is about the energy conditions. You can also look, for example, at the weak energy condition. Basically, what we did in this case was just, obviously, you cannot verify all the possible observers, so you can choose one and try to see if there's some violation or not. So in the case of a zero angular momentum observer, you have to check if this quantity is always positive. And then you can also look, for example, to the strong one, the strong energy condition, and for the zero angular momentum observer, that equation must also be always non-negative. So you can do this, and essentially, in this case, I don't believe any of these quantities are violated. But for example, for axionic boson stars with a decay constant small enough, so start to have different type of behaviors, the strong energy condition can indeed be violated for this specific observer. But for this particular case of the mini boson stars, you can see the weak energy condition, at least for this observer, is never violated. And the strong energy condition for this observer is also never violated. So, okay, in the end, you can just do some prints and, okay, see, okay, in this case, okay, the mass, the ADM mass, so the mass computed through the asymptotic behavior is this one. And in this case, since the boson star, since it is a boson star, this will be exactly equal to the Komar integrals. So as you can see, they agree quite well. The same for the angular momentum. Then you can do, for example, compute the reduced angular momentum and the spin of the boson star. Then here you can see the compactness. Since the inverse of the compactness is bigger than 1, it's less compact than a black hole, as it should. We have two Eger regions. So the inner edge appears at this radial coordinate, and the outer edge appears at this one. Not very important, but then you can look also to the stability, the structure of cyclic orbits. We saw that there are no prograde light rings, but there are two retrograde light rings. Then you can look at what are the radial coordinate. And then we also saw that there is one prograde ISCO, which is exactly the same as the retrograde one, since it's defined in this case by the fact that the angular velocity starts to be complex. But in the retrograde case, there's also a marginally stable cyclic orbit, which I call MSCO, but in discussion with Pedro, we thought a different name, and you can call it MASCO, to be a bit easier. And then, in this case, for the zero momentum observer, the weak and the strong energy conditions are not violated. So that's something that you can do. So this lecture, you can at least get some idea how to start with the solution that you obtain, and then try to use this type of machinery, either with Mathematica, with C, with whatever language you want, to start to obtain some physical quantities. So thank you very much for your attention.
So thank you, Jorge.
Thank you.
Do we have any questions online? No? Do we have questions from the audience?
It's easier.
Thanks, Jorge, for the very nice course.
Thank you.
So, for the boson star case, you solve the equations until r equals to 0, right?
Mhm.
But for the black hole case, you solve just until the event horizon.
Yes.
So, can you solve also for the region inside the event horizon to have some insights? For instance, are these black holes regular or they are singular, like Kerr?
No, at the level of numerics, you can. If you define everything well, if you define the boundary conditions well, and so on, I would say so. But you can expect that there will be some singularity within the horizon. So, but you could do analytical continuation if you want. I think at least at the level of numerics, but it'd be tricky because one of the boundary conditions will be at the singularity. So.
Yeah.
Can you think or can you prove that there is a singularity without solving the equation?
Well, if that, that's a trick question. Well, if you have, I don't know.
Think about Bedouin's scale.
Yeah, I know. If there is an event horizon. Mm-hmm.
There must be.
Yeah.
If there is an apparent horizon,
there's a singularity. Mm-hmm. Yeah.
Except that, of course, it's geodesic incompleteness rather than singularity, like curvature, but they
No.
coincide.
Yeah, but
Yeah.
there are also other details because when these solutions are very non-Kerr-like solutions, so the singularity can be very different from the Kerr case, right?
It may be.
Yeah, yes.
But the existence of the singularity. So
Yeah,
if
the
you're asking about the
existence,
existence, I
yes,
would say
the-
that this is guaranteed.
Yeah, probably,
Yeah,
yes.
but the nature of the singularity may be
Because,
tricky.
yes.
In fact, let me comment on the following. So there are some studies in this direction. And one of the characteristics of Kerr, like Horizon-Nordstrom, is the existence of an inner Cauchy horizon. As we know, this is an abstraction of the eternal black hole, because in practice, at least for asymptotically flat spacetimes, there is this mass inflation phenomenon, which makes the Cauchy horizon unstable. What we think is generic is that the presence of this matter field, like the scalar field, actually triggers something similar so that you do not have a Cauchy horizon. Indeed, you'll have a space-like singularity as in Schwarzschild rather than something like in Kerr. So we've seen this with Eugene and Yves Prier in the 5-dimensional analogs of these black holes. Because in 5 dimensions, you can have these solutions where they are spinning into planes and therefore they still are codimension 1 in the sense of having just radial dependence. So it's easier to integrate in. There's also some work by Horowitz and Santos in some similar systems where they see more or less the same thing. So the inner structure of this hairy black hole seems to be more Schwarzschild-like, and therefore not having the Cauchy horizon. An interesting question is then what happens when you go to extremality. That's another interesting question. And, yeah.
Okay, thanks.
Thank you. Any more questions?
Thank you very much. You mentioned that the solver finds solutions with m non-integer, and you say that you neglect them.
No, what? Sorry?
Neglect them. But why do they even exist? Do you have an idea?
Physically?
No, in the code.
No, I
Because
think
the code finds them, right?
Yeah, but I think you can find the solutions. You have a solution. But
why?
At the level of solver, it doesn't care exactly what is the physical meaning of the having of integer m. So you can find the solution. It may be not physical, but not even physical significance. But the solver can find it. It doesn't know or doesn't care exactly what if the m can only be positive or integer, or it can be any real number. It only if there is a solution, it can converge to that and it gets something. And then you can use that to increase up to 1, but those solutions in between would probably not be any physical meaning. That's my idea, not my intuition. But maybe Eugene can also interfere. Okay.
Problem with a non-integer winding number, m, is from a different direction. It will not be analytical function. It's period of 2 pi for the...
Yeah.
But technically, solver is blind.
Yeah, he doesn't care if it is or
Doesn't
not.
care about this extra feature which you see when analyzing the geometry and the consistency. But technically, it's just a parameter. Equations.
If I may just add a comment on that, because you see, locally there's no problem somehow, because it's a periodicity problem. So it's a kind of, yes, you'd be not having something which is, well defined if you go around, but locally at each point it's well defined. And since you're not trying to interpret the solution, that's okay. So locally you're getting some local geometry, and then you're just building up on that value of m until you get to the value that really matters. So it's kind of a trick, but it works.
At the level of tricks, I can also give you a different one, which is regarding the backbending of the solutions. So for boson stars, let me erase this, you have the typical in spiral. So we have here omega and m, and you get something like this, right? So from my everything that I said, that okay, this is m equal 1. You start, for example, here with this fixed omega. Then you change omega, and you get these solutions. You go up to here. How do you go from here to, or this first branch, to the second one? It's a bit tricky, because if you start with this one, this minimal frequency solution, and you change again to a smaller value, instead of going here, you could go back. So how do you go to this second branch? A trick, as Eugene told me, and teach me, is to try, okay, let's see, have here the backbending, have this solution. You try to find a solution here that doesn't exist, so the solver will not converge, but it will give you something, and then try to use that one to go here. Does not always do what you want, so not always you can go from here to start to have the second branch, but it can help, and sometimes it works. So it's just a trick. Obviously, this doesn't have any physical meaning, just something, and if the solver not even converges, but it's something that can help you to find other solutions.
So, thank you. Any more questions? No? So let's thank the speaker again.